Okay, so I hope everything is working. I'll give it a last check. Click here, click there. Yes, so it seems we are set. So let's give it a couple of last seconds and then we will start the webinar. Okay, so I think it's time, so let's start. Hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we will talk about engineering simulations. Today's topic is Kaplan turbine. We will talk about specifically about CFD and also about FEA, FSI, very little bit about optimization. So let's see, let's discuss everything. Yeah, so the webinar is being recorded. The recording will be later made publicly available on our YouTube channel. So yes, so it will be, the recording will be available. There will be a couple of parts in this webinar. In the first part, there will be a general introduction where I will generally speak about our software and about our company. Then in the second part, there will be a more practical part where I will talk specifically about CFD simulations applied on the scenario of Kaplan turbine. And there will be also the last part where you can ask your questions. Feel free to ask your questions anytime during the webinar. There's a special window in the GoToWebinar client, so you can write there your questions, and I'll be happy to answer all your questions, especially those questions which are relevant to the topic and which are interesting also for the audience and for the other people in the webinar. And the specific questions will be answered later via email, but you can be sure that all the questions will be answered. So I hope everything is working well. If not, please let me know in the questions. I will check them regularly in regular periods during the webinar, and I will react if something goes wrong. So I hope you can see us and or see everything, and let's start. Today it's just myself. Radek, my colleague, couldn't make it today. He's on well-deserved holiday with his family. So many greetings, and for sure at least his spirit is with us today. But today it will be just me. So I will guide you all the way through. It will be a little bit different than usual, but I hope it will be a lot of interesting points and a huge amount of value for you and your engineering simulations. So let's get into the action. Yeah, so there will be a lot of other webinars. So for example, in September, we will talk in the next webinar about remote computing. So yeah, the next webinar in September. There will be a webinar about pumps later on, and also about external aerodynamics and about compressors, and again, Hydro turbine, Francis turbine. There will be acoustics webinar in November, and wind turbine webinar still this year, and also blood pump webinar, and perhaps we will insert a couple of other webinars. So definitely there will be a lot of webinars. So feel free to send us your questions and ideas in advance, and then we can focus on the answers and on your topics, and we can dedicate specifically our efforts to your topics. I hope it's clear that CFD Support is the name of our company. We are like 15 years in the market. We are located in Prague, Czech Republic, and we have connected our, I would say, careers to CFD and also to to other engineering simulation fields as everything is extending and the workflows are becoming more comprehensive. It's also about FEA and FSI. It's quite a lot of about optimization nowadays, and also we do our golden egg is acoustic simulations for the external aerodynamics and also for turbo machinery. So we definitely deal with engineering simulations both on software side and also on consultancy side. We typically transfer our knowledge to our users in way of software or in a way of consultancy projects. Our main, I would say, flagship product is called TCAE, which is a comprehensive simulation environment where the users can run their simulations and maintain their also knowledge in it, which is more and more about the knowledge. TCAE software consists of software modules, so for sure not everything is needed for everyone. So there are modules, specific modules, which are dedicated to specific parts of the workflow and the results. TCAE is extremely flexible, so the users can, it's really like a puzzle. So the users can pick the modules and they can join them or connect them to other existing workflow, other existing software, whether it is a commercial code or an in-house code or another open source. These CAE modules are extremely flexible and ready for this and to be used inside an existing workflow. So there are a lot of examples we did with our clients, and so it's definitely usable in many ways. Yeah, the license is typically unlimited, so there are no limitations on number of its users, job scores, hardware installations. So you can be sure that you can use your resources to the fullest. The CAE is very accurate because it's dedicated specifically to turbo machinery applications and also to external aerodynamics. So it's not a general purpose code. It's a code which is focused and it allows it to be accurate. And it's well automated. Automation is a big thing, of course, and automation is our big topic here at CFD support. So we can be sure that TCAE is perfectly automated and can be scripted, and there are many ways how to run it. So automation is a big thing. There are a lot of benchmarks we did in the past, so they're ready for them. Most of them are available for public presentations, or I mean, these are these are available for public presentation, and there are tutorials. There's good technical support. So we believe TCAE is ready for professional usage in the industry. TCAE can be run remotely, of course. It can be run on laptop, desktop, on a cluster, on a cloud, from home, from work, in Linux or in Windows. So there is almost infinite freedom of its usage. TCAE is based on open source. There are a lot of open source packages in it. Last time we counted it, it was like 65 open source projects in TCAE that allows us to develop it very quickly because all the open source codes are being developed, and on top of them we add our engineering skills, experience, and effort for turbo machinery applications and for the external aerodynamics, and that allows us to go quickly forward in a relatively small team, what we have here in Prague. So we are very, very sharp in this because the codes are being developed, and we put all the best of open source together and prepare it for professional usage in the industry. So for your information, we've spent far more than 40 many years of focused development in a team, gathering all the market experience to make the product like coherent, consistent, and really working. Okay, yeah, there are always some new releases. We are now finishing the next release, which will be released in October. The current stable version is 24.3, which has been released in April. And yeah, so there's always a lot of new stuff we are developing in a very quick pace, and hope we will keep the pace for some time. Yeah. Anyway, today's webinar is dedicated to, I would say, hydro turbines, specifically to a Kaplan turbine, and what we can do. I will now switch to the next part of the webinar, so which is kind of practical presentation. First of all, I would like to say that I will take it quite easy. I will say a lot of general information. I will be general. I will talk quite a lot about principles to give you like the whole picture, which is my typical topic. So I'll be very general, but there will be, I believe there will be still a lot of takeaways for you. So okay, so I will start with a recommendation that I recommend to everyone to start with goals, because it's always extremely important to start with where you want to go and what you want to achieve. It's very important, and it's perhaps the most important recommendation I give you today. Start with goals, because it only matters if you have clear definition of your goals, what you want to achieve, why you are going to make any engineering simulations, because it's similar to life. If you have no clear specific goals, if you do not know where you are going, you will never get there. So start with the goals. It definitely makes sense. Take into account what are your aspirations in terms of speed, in terms of accuracy, in terms of robustness. Take into account what's the difference between one-time project. For example, if you are doing this simulation just one time, you need to grab the results and run away. Or if your simulations are repeatable, are you going to repeat them one time, two times, or for a lifetime? That's a really big deal. Is your case standard? Has this been done million times in the past, or is this too specific research project you want to really explore something which no one has done before? It's really another big decision, right? So start with your goals. What are your goals? So yeah, so I'm switching to the software now. So yeah, now I hope you can still see everything what I'm showing here. So this is a simple model of Kaplan turbine, and my typical goal, I want to start with goals, might be, let's say, okay, increasing the efficiency. Okay, so let's say okay, this is just a dummy example, but okay, my goal will be increasing the efficiency, and you should be able to decide how much you want to increase it. So for example, okay, my goal can be I want, for example, in hydro turbines, 1% of the efficiency, it's huge. I would say a huge amount of energy, right? You can always recompute it to the energy. So 1% is quite a lot. The good news is that for hydro turbines, we are able, or the engineers are able to make simulations that are extremely good, which are extremely accurate. They're nearly perfect. So you can meet the benchmarks in really closely in I would say 0.1%, right? So your goal could be, I want to increase my efficiency of my, for example, design or early designed Kaplan turbine by 0.5%. That's a clear goal, and you can launch a project which has a goal to increase the efficiency of your particular early design of Kaplan turbine by 0.5%. That's a goal. It's reasonable. It's achievable for everyone, or of course it depends what's the early stage of Kaplan turbine design. But anyway, it's clear and it's achievable. But anyway, I'm getting back. You always have to start with goals. Goals are extremely important, and you should be aware of where you want to go. Okay. Then I will say a little bit to phase which we call pre-processing. I will just start with pre-processing is a specific part where you want to receive, I would say, simulation ready geometry. And some people include also the meshing phase, which is creating the 3D volume mesh for your model. So I'm friend of yes, including the meshing phase to the pre-processing. So I personally, if I say pre-processing, I also mean creating the simulation ready mesh, which aspires to have good, which has the potential to give you good simulation results. So pre-processing part, let me say a little bit about this. So for professional CFD simulations, you typically have 3D geometry, which is created in some CAD system. And this 3D geometry is not necessarily a simulation ready geometry, right? It's the data representation of your model, but it's far away actually from being able to be directly simulated. And this pre-processing phase should get you over the process when you clean the geometry and make the relevant parts of the model available for the simulation. And that's typically a bottleneck, especially for the beginners, right? The beginners, for all of us, of course, but for the beginners, it's a bottleneck because these preparation of input data of the inputs, the input data, it's sometimes difficult because you have to play with I would say CAD software and that's typically a problem because we do not do it every day, and what it's like muscles, what's not being done every day, it's sometimes difficult. Okay, so the simulation, the pre-processing, your goal is to create watertight components of your model. So I will show you what I mean here. So I would say a simple, I would say very simple turbomachinery here, specifically a Kaplan turbine, can consist at least, I would say, from 3 parts. I'm talking here about quite kind of realistic model. So at least you would need 3 parts, and these parts we call them components, right? So these components, in this case, we call them. This is by the way, this is tutorial which you can download on our website. So it's freely downloadable. So there you can download it and open it in standard ParaView or in TCAE, and then you would completely understand and you can play with it and you can simulate it yourself. So this case is completely open, including the results and everything. So I'm talking here about Kaplan turbine, the specific tutorial, and you typically need to separate it or split it into the components. Why? Because for turbomachinery, if some parts are rotating and some parts are static, so you need to separate those static parts from the rotating parts. So here we have the simplest possible division the split of the model into the parts, into components, and we have the spiral, we have the component called wheel and the component called draft tube. So let me just show you a little bit that typically any component has its inlet, it has its outlet, so those are the interfaces. Those are like virtual faces where the fluid flows in and out, and then it has a wall and or a couple of walls, or so it's the interfaces and walls. That's very important. And what's also very important is that your components should be watertight. So if you pour the water in them, the water should stay. There should not be holes, and it should be really watertight. So that's a relatively strong requirement, but there are not many those requirements. But this one is extremely important. So you need components which make together the model. And the components should be watertight. And second requirement is your interfaces should match. So for example, this spiral has the inlet, which is this blue part, and it has its outlet, which is this green circle or rounded part, and it has to match with its neighboring component, which is another component, which is, for example, this component called, we call it wheel. There is the impeller in it, and the interfaces has to match. Of course, we are not having the volume mesh yet. We are just talking about the surfaces and about their topology. But the interfaces should match also, because it allows you the conservation of the flow or of water here. So splitting in the preprocessing, you have to split your CAD model into watertight components, and the interfaces should match. Yeah. So the first part here for the Kaplan turbine is the spiral. The second part is called wheel or the impeller, and the last part is called draft tube, which is again 1 or 2 or 100 walls, and the inlet interface and the outlet interface. You can have any number of them, but they should create together the component which is watertight. And I hope it's clear that I'm talking here still about just the surfaces. I'm in 3D, but I'm talking about surfaces, right? The mesh, the volume mesh, so the cells volume mesh will be created later in the process. But again, it's important to say that this pre-processing part, this cleaning part, is extremely important, because it sets all the aspirations and all the expectations right here in the beginning. So, for example, poor engineering or bad input data cannot, I would say it cannot be, or it can be hardly compensated later in the process, right? So you have to have a good model in the beginning. Sometimes Radek, my colleague, says garbage in, garbage out. So if you have poor data in the beginning, it can be hardly compensated later in the process. So the principle is very simple. You can forget all the tiny, irrelevant, small pieces. Just that's not important, but it's important to have a good representation of relevant surfaces of your model. When I talk about the Kaplan turbine, it's important to say that you can have any number of surfaces. So for example, professionals use for example split the impeller to hub and shroud, and also the leading edge and trailing edge, and pressure side and traction side. So it allows to use advanced methods like mesh refinement and also the evaluation in the post processing of the results. But those are perhaps too detailed information for this webinar. So I will go ahead with this information that you have to have watertight components, the interfaces should match, and it's good enough to have I would say quite good results. Okay, so still in the pre-processing, when you have these I would say parts, you can decide. Yeah, I had to say in the beginning that I'm working here that we will create the mesh here, right? So we create mesh here in TCAE, which is it has its meshing tool based on SnappyHex mesh. It's extremely robust and extremely effective and easy to automate. And of course, you can, if the users like to, they can import the ready-made mesh which is created in another external software. So that's okay. So mesh can be either loaded, the ready mesh can be imported, or it can be created here automatically. So we, as a first choice, we recommend to create it in TCAE, but the final decision is always on the user. So yeah, so when I have these surfaces, I decide what is rotating or what is not rotating. I load these components here in the T-mesh module, where one by one, where I say what is blade, what is rotating, how much it is refined, and what is the input, what is the output, and what are the interfaces. That's very important. And that's I would say the basics. What I would say. Of course, you need to know what's the inside, what's the outside. You should be able to say, for example, what's your background mesh, what's the basic what is the basic cell for size, for example. Yep, I have this IDOM view, render view, which doesn't show a good background mesh. Okay, so I will switch it off. Anyway, the meshing settings, you do it here in the T-mesh module. You decide what's your basic mesh size, and yeah, that's, I would say, maybe this could be enough. For this, there are a lot of options. I'm not going to go for the details right now. But yeah, the volume mesh is created out of the 3D surfaces which are loaded from the CAD system. That's important. I'm friend of simple solutions in the beginning, so I always recommend to create simple meshes, small meshes, to make sure everything is running, the workflow works, and especially I recommend small meshes in the beginning because you can refine them anytime in the future, and later, I mean, and later you can refine and the issue with the fine meshes is that it takes a lot of time, the convergence process, and then you're losing your time. So I recommend quick iterations in the beginning on the rough mesh, on the small mesh, and then refine when you are sure that the model is performing the way you would expect. Okay, so these were my recommendations for pre-processing. So I will go a little bit ahead to the simulation settings and run. So again, there are a couple of decisions you have to make. So once you have the simulation mesh, I didn't do it here. I mean the mesh practically, but I believe it's it's clear. The simulation settings, you can do it in the TCFD module. So TCFD is the part where you set the simulation. In the beginning, I would like to say that for the beginners, there are a lot of parameters that may confuse you or confuse the beginners. So don't worry about them too much. In the beginning, you do not need to know many parameters and many settings. There are only a few of them are important, and later, as the experience grow, then you can add more and more details and get into more and more complexities. But in the beginning, it may confuse, but there are a lot of parameters, but not all of them are equally important. Some of them are extremely important, and the rest is not that important. But for every simulation, you have to decide something what we call time management, which means that how or at least what I'm going to simulate. The first critical decision is steady state versus transient. Steady state simulations are quick and fast enough to see a lot of, I would say, simulation points, and transient simulations are more, I would say, comprehensive in accuracy, and they're important for special physics. For example, if you want to include the cavitation, then you would likely need the transient simulation. So the first decision is steady state or transient. They have both their benefits. So you should be aware of this. So steady state simulations are very likely those simulations you would start with. Then you can decide how many points will you simulate. So for example, with hydro turbines, for Kaplan turbine, we typically simulate speed lines. That means that for one speed of rotation, we select, I would say, here we have 10 points where we will simulate iterations. So the result of the simulation is like the characteristic which are the characteristics which shows us one speed line at 10 I would say lots for the turbine. So the time management is extremely important. Time options, extremely important. Yes. The physics needs to be decided. So for hydro turbines, you need to have the incompressible model. You can decide some fluid properties and various options. Not of them are that much important, especially in the beginning. You need to know just a few parameters, and the solver is decided by the time management. So it's incompressible and steady state. That's important. A good point is, for example, turbulence is very interesting. Typically, the beginners overestimate it. It means that they think it's all about turbulence. Yes, turbulence is important, but not in the beginning. So that's a little bit tricky. We call it turbulence paradox. So yes, turbulence is extremely important parameter, but maybe not in the beginning of your simulations. It decides the final accuracy. When you have already something which is really good, then with turbulence you can make it perfect, right? But very often people think that the turbulence settings are important in the beginning, while boundary conditions, which are way more important, extremely important, it's something which is set automatically. But it's the opposite. It's the other way around. For example, boundary conditions are extremely important because they specify the task. It's all about the boundary conditions, and it's much less about the turbulence for those who begin with simulations. Okay, so yep, so you should decide a couple of settings here. I'm not going to go too much to details. The TCAE has really good defaults, so default settings already is preset for typical, yeah, for hydro turbines, for example. So there are simulation types, and if you select a hydro turbine, you have already preset really good options which have worked in the past a lot. So as I mentioned, what is extremely important to specify is the boundary conditions. So typical Kaplan or hydro turbine is run with flow rates. That means I prescribe the flow rate at the inlet and prescribe the static pressure at the outlet, and those are typical boundary conditions. So for this particular tutorial, we have a set of, it's one speed line of 10 points. So we have a characteristic of flow rate which starts at about 100 cubic meters per second. So it's a large Kaplan turbine with double regulations, and we have 10 consecutive flow rates that are run in the simulation. That's important. So inlet, outlet, and these options are very important. So boundary conditions. And also what's important, what needs to be decided, those are the outputs for the post processing, right? So for example, you can in the graphical interface, you typically are interested in what are the residuals look like, what's, for example, the efficiency. It could be my goal for the project, as mentioned in the beginning. So for example, in the line chart view, you can put the quantities you would want to follow. So I'm specifically interested in the efficiency, how it develops during the simulation. So you can set it here, and also in the menu there's menu called post processing, and for the report you can set all those various units and views which can be set, and later will be written down during the simulation or at the end of the simulation, and you'll be able to follow them. Okay, so the simulation setup is you typically do it one time, because when it's done first time, then you can always use it again and again and only improve things what you think might be important for your next case. But the simulation settings and run, you typically do it just one time, and then run the simulation. So the simulation is being run once you're fine with the settings. By the way, yep, you can do the same with FEA simulation. So FEA simulation is the principles are the same. You can, yep, you do the mesh, which is created typically in NetGen or GMSH, and for FEA analysis, you can again you have the surface which is being meshed, and FEA can do the analysis of the structure. So here we have the blades which are loaded. The forces from the fluid flow is transformed to the blades as a static load, and FEA analysis can give you for example, analyze the stresses. It can analyze the modal analysis, or for example the deformation. So it's it's FEA. The principle is very the same, and also the settings is the same. The solver is Calculix, and there are a lot of settings, but you do not need to worry too much about that. There's a lot of settings because only a small part of all the settings is important. Yeah, so it's the settings, and to run the simulation, finally you use this. Yeah, on the top of the project you run is yeah the manager where you can run everything automatically, or you can create the meshes component by component for CFD, for FEA. Then you can go for the simulation run of again one by one, or automatically. You let it run, and then you basically yeah, have the simulation finished. Okay, so the simulation settings and run. The next typical phase in the engineering simulations is post-processing. It's a really important part, and from my experience, it's often underestimated. So people think when they have simulated, they have the results and it's done, but to understand the results, why the results are they are, and to play with them and take the lesson out of them is the post-processing part, and sometimes it's the most critical part, especially for advanced projects. It's while for the beginners the tricky part is pre-processing. For the advanced users it's post-processing, because you have to understand the results, and that's sometimes an issue. Yep. So you can watch everything, right? So it's all the data are extremely transparent. So you can watch the volume fields. Maybe I can show a little bit of them. So I will open new render view. I will take a look. I will open some volume fields to give you an idea what we have. So okay, so this is already the volume mesh. So I have opened the volume mesh. You can see it has really the cells, the pieces which it consists from, and this is for example, the pressure, and you can play with it. You can play with all the options. The ParaView is particularly very strong for the post-processing of the volume fields. So you can use countless number of filters. You can use countless number of various sources and plugins which show you what has been simulated. I will make some quick maybe slice to see the what maybe this meridian somewhere in the axis. Let me try to show this. Okay, so this is yeah, for example, the pressure field in the central plane. You can see that yeah, it's a turbine, so typical I would say machine that consumes the energy, right, to create the energy, to turn it into the electricity. So the big pressure above the impeller, and the impeller consumes the energy and gives you back some little, I would say, little energy back, and the calm water flows away. And you can do the same with a lot of quantities. Perhaps I'm not going to go too much in detail, but yeah, this is what you typically can follow. And this is yeah, these are the volume fields. There are a lot of quantities you can look at, and there are even more quantities you can evaluate. Here, as I mentioned, ParaView is particularly very strong for post-processing of the results. There are really a lot of tools what you can do. So these are volume fields. You have what is very useful is the HTML report. So this is what we added to TCAE. So every simulation has its report where you see exactly what has been simulated, when, and you can see various simulation stats, what has been exactly what has been simulated, how it has been simulated, what are all the parameters, what are the times, and what are the all those simulation parameters and results. You can see how everything or how many quantities have developed in time. You can load your data, for example, you can see directly the comparisons of some reference data, if you like. So there are a lot of information, including various forces, and of course the efficiency, the head, the flow rates on every interface, how the pressure is spent, how it goes through the through the machine via interfaces, what are the velocities, how they change, and there are various angles, how they change. The various averaging and averages. There are also, even for steady state, there are some cavitation assumptions by some models. So there are a lot of specific statistics and results. There are also possibilities to evaluate the blade-to-blade view. So you can like unwrap your impeller part to see spans between the hub and shroud. And there are also meridional averages that can show you how in the meridional view, how the for example the pressure is being spent, how it's distributed without the average is circumferentially averaged to a plane. So there are a lot of options, what to print, what to follow. By our experience, every engineering office has its specific views. For example, the angle at the leading edge, or the blade and its contours of pressure, etc. There are a lot of views. Every engineering office has its different views, and this is a universal tool where you can use them all. Okay, so post-processing is extremely important part where you can preset everything and then just use it in the automated workflow. Finally, I have a couple of tips and tricks I would like to share with you. I mean, these are kind of experiences we have gathered along the way over those 15 years, which we are in the turbo machinery business. Important thing is that almost anything can be automated. So do not worry too much about the things are difficult to click and set and everything, but almost anything can be automated. So it's possible to include various scripts and all the stuff, save all the settings and make it better and better. So it's maybe, everything can be automated. Another point I would like to share with you is it's rather a marathon than quick sprint. right? So you over the time you gather more and more experiences, and that makes you better, right? So it's not a in engineering simulations, it's very difficult to make good projects quickly. It takes time, and really the experience, they are like aggregating. It's like a snowball. It's as I mentioned, yes, it's difficult to make great projects quickly. Yeah, that's definitely the point. If you bring the more multi-physics you bring, it definitely brings another level of complexity. So I always recommend to start with small projects regarding the settings, the goals, and the meshes and everything. Start with small and accumulate and aggregate the complexity later in the process. But I would recommend even here, when we do some consultancy project, we start with something as simple as possible, and then we make it more complex and more complex. Yeah, because complexity brings problems in every project. So multi-physics brings a lot of complexity. The same as acoustics. Acoustics also brings a lot of complexity, but it's not important for Kaplan turbine. Let's go ahead. Yeah, you can, when you're pretty much sure of what you are doing, you can employ the optimization, right? To optimization typically in engineering simulations means run a lot of a loop of a lot of simulations in a loop, which they can iterate towards your best or towards your goals or to the best results. So again, optimization is great tool. It's definitely the future of repeatable simulations, but it brings again another level of complexity. So once you have good simulations, you believe in them, you trust them, then you can use the optimization, but it's difficult to start with it. Yes, my hard, I would say, experience is that that's something what people very typically or often confuse, is that the accuracy, for example, is very much depending on the effort you spend with the project, right? So it's similar to life, where you spend a lot of effort. It's like muscles; it grows and gets better and better, and it's difficult to get great projects quickly. So this is the example, what we called, it's the accuracy versus effort. And with the effort here, we mean that effort is some specific decisions, or I would say those are problems you have to resolve to the particular quality, right? So for example, if you have I would say very simple simulation, very simple problem, you have to decide only like something like 10 decisions. So you make I would say 10 resolved decisions. So you choose the solver, you choose the boundary conditions, you choose the mesh, which is not bad, you choose the turbulence model, you choose the geometry representation correctly, and then you already can receive something which is 10% far away from the ideal results, right? We have this accuracy level, which is the in percentage, it's a deviation from the perfect results, right? So this 0% is it would be perfect results. Nobody knows what perfect results is, right? But you can you can, it's some beliefs, and you can get closer and closer to them, right? So with 10 decisions, you can have something like 10% accuracy. The problem is that we are facing here and I would say geometrically or exponentially growing problem. So if you make another 10 decisions, you can okay, if you make, okay, let's say 15 decisions, you get 5% closer, right? But to get another few percent closer, you have to make more and more decisions correctly. And if you want to get somewhere like 1% close to the perfect results, you have to make maybe hundreds of resolved decisions which are based on a really good estimation. So that means that you're facing a problem with more and more effort. You're still getting closer and closer to perfect results, but not linearly, right? So that's quite a big deal. So it's an exponential problem, right? So if at the end of the day, at the end, after a few years in the simulations of hydro turbines, if you want to resolve by 0.2% what you had before, then you have to spend twice the time than you did before. So I hope this is clear. So effort, so you can have some results with little effort, but perfect results with endless effort. So I mean infinite effort. So it's this is really an issue for the simulations. And the problem is also with the reliability of CFD results sometimes, because you never know how much effort has been spent on what results. So if someone shows you the results, you never know how much effort has been spent on them, and sometimes it's those colored fluid dynamics, and sometimes it's results someone spent a lifetime on them, and it's difficult to make any judgments, right? So sometimes it's tricky. Okay, I will go ahead. So another my heart point is that technology is only about 40% of success. Here I mean that the software, for example, our software or some other software, it's only 30% of the picture. The rest is your skills, your experience, your patience, and your dedication and your effort, right? So typically people overestimate the software, what results it gives, and overestimate their contribution to the project. But the experience teaches us that it's far more about the engineers than about the technology that they use. Typically, software, with any software you can do any results, but it's the engineers who make the projects, and that's typically an issue. So it's very important to take care about also the technology, and also who and how is being used. That's really a big point. Yeah. So I would there for sure there are a lot of things I could talk about, but now I would like to ask you, the audience, to ask your questions. I'll be happy to answer any of them. So yep, feel free to ask your questions. I'll be honest with you, I can't see many questions so far. I can see quite a lot of people here, but no one is asking. So what do I say? I haven't prepared any typical questions. So what would you like to see? What would you like to know? Of course, there is, it's the simulations are extremely complex, right? And it's difficult to estimate where exactly you are on your on your journey with simulations, but it's definitely a marathon. There's nothing like quick wins, and there's nothing like quick results in this. Yep. Yep. So yep, I have this question. Yeah, that's great. Susan is asking whether it's possible to do geometry modifications. It's a good question. It's a good question, and unfortunately, I have a negative answer. No, in TCAE you cannot do any real modifications of the geometry. You can play with mesh. You can have some settings, but the real modifications can't, unfortunately, be done in TCAE. For geometry preparation, we recommend, because all our software is based on open source technology, so we also recommend and we use the Salome project. Salome is relatively good. It's open source, it's free, and it's specifically good for creation of the surfaces for the simulation and for geometric cleaning. So we recommend Salome. It's free and it's fair. And we also know that, for example, a lot of people use Rhinoceros, which is a commercial code. It's a commercial CAD, but it's not expensive at all. So every business can allow a license, which is lifetime license, and it's extremely powerful, and it can be parameterized, and you can use the parametric model in there, and then it becomes really interesting in terms of optimizations and other stuff. So for those who do not want to invest, Salome. For those who can allow some investments and are professionals in every way, then Rhinoceros might be an option. Yes. So what else? What else? Yeah. So yeah, there are some. I can see any other questions, and I feel that I should do something, and I don't have any questions, so I will go ahead. I will thank you for your attention. This will be it. Feel free to ask your questions anytime. So this is just, yeah, ask your questions anytime. Send us an email or call us or anything. We'll be happy to answer any questions. So we can do it later. So if you have any interesting topics, questions, or anything, just let us know, and we will gladly come back to you. And I guess this will be it for today. So I will leave you with that. Enjoy the hot summer. Enjoy your holidays if you still have some. And yeah, see you somewhere, sometime. Thank you. Bye bye.